Hello, and welcome back to CS422 Theory of Computation. Last time we talked about the famous Immerman-Szelepscenyi theorem, which is so famous that not only does it have its own name, which includes the names of its inventors, of its detectors, but also which was awarded the Gill Prize. So, and it's the proof is a very complicated and ingenious construction of a memory efficient algorithm. This is what we're talking about here in chapter 5, algorithms that use little memory. And this is perhaps a new paradigm to you, certainly when you write programs, when you're asked to devise algorithms. In many parts of computer science, speed is the most important property, running time, fast algorithms. But there are also cases and applications where memory is the constraint. So here you can consider chapter 5 as a lesson, as a training in devising memory efficient algorithms, which is gives a very new perspective maybe. For example, for memory efficiency, it may be advisable to recalculate things so that once you have calculated some intermediate quantity, maybe you've spent a lot of effort in calculating some intermediate quantity, but in order to save memory, it's maybe preferable to discard, to relinquish that memory. And once you need the quantity the next time, to recalculate it again, because in this paradigm, we're not really concerned with the running time of recalculating, but we're concerned with the memory consumption. And this is a new paradigm. For example, just one example is a router, right? So a router in the internet has to process immense quantities of data, but it has very little memory compared to the amount of data that is passing through the router. And that's an example of memory where memory efficiency becomes key. But there are many more examples. For example, these microcontrollers, also usually equipped with very little memory, but have to run for a very long time. Well, actually, they're supposed to run indefinitely. They're not supposed to ever stop or terminate. So this is another application. And we have seen examples of such algorithms. One example being the Savage algorithm for deterministically deciding reachability in graphs of exponential size, or without, of course, without storing the graph, because that would exceed the polynomial memory bound. So that was one important technique is recursion, because in recursions, when we have several recursive calls on each level, we can reuse memory throughout each of the recursive calls. That's one important technique that you may want to take away from this chapter 5 beyond the complexity theoretical aspect. Namely, we're basically talking about the millennium problem, P versus NP and its variance, NP versus P space. This is the other perspective of this chapter, NP versus P space. So, and since the Immerman-Szelepscenyi theorem is so involved, let me use the opportunity to have a recap on it. So what you see here is the statement, namely that NP space is the same as co-NP space. So where a Savage theorem would insert that NP space is contained in deterministic quadratic space with a quadratic overhead, Immerman-Szelepscenyi says that NP space is contained and by symmetry equal to co-NP space without polynomial overhead with only a linear overhead that is indicated here in this big O you see here. And remember that co-end space means the complement of non-deterministic space algorithm. And the essence of non-determinism is you can guess, but you have to verify. And if the verification fails, you have to abort the program. You may only continue, terminate, and accept once everything has worked out through all the guesses, which is a great opportunity. Another interesting paradigm in algorithm design, this non-determinism. And for the reachability problem of this graph, which has exponential size and therefore again cannot be stored here, the reachability problem, that was our first assumption, is easy to solve in linear memory by repeatedly guessing vertices along the path, but by discarding all the vertices previously visited on the path, because the path in general may have exponential length. So this allows to store only constant number of nodes and still be able to find a path if it exists. And then verify that within the given number m of steps, one has indeed reached the target vertex. But for Immerman-Szelepscenyi, for co-end space, we need to somehow be able to solve the unreachability problem, the complement, the negation of the reachability, but again, using only positive guesses. And that's the challenge and the ingenuity of the Immerman-Szelepscenyi algorithm. And so that was item A. Reachability was kind of a warm-up. And for unreachability, we would consider two further intermediate claims. The first intermediate claim is if we can or compute, or if we know the number of nodes reachable within a given number m of steps, then one can also non-deterministically guess and verify that a given node is not reachable within that number of steps. So here, the item P, there was the implicit assumption that this number as a function is computable in non-deterministic linear space, where non-deterministic computation, as you call, meant that we can make guesses, but at the end we have to output the same value, namely n of m, for any possible successful choice of guesses, whereas for any unsuccessful choice of guesses, again, we have to abort the computation. And the final claim says that indeed this number function is computable in non-deterministic linear space. So by combining these two claims, really the Immerman-Szelepscenyi theorem follows. But we've deliberately introduced these intermediate claims because they kind of climb up and become more and more evolved with the algorithm. So let us briefly recall the algorithm. The algorithm for guessing and verifying unreachability under the hypothesis that the function n is computable in this non-deterministic linear space. And the key here is to somehow, logically speaking, non-determinism is kind of amounts to an existential quantifier. Remember, in non-deterministic polynomial time, this was captured with a syntactic definition where the existential quantifier ran over the all possible witnesses, exponentially many witnesses of polynomial length each, and similar here. But unreachability naturally is about the complement, the negation, which according to De Morgan's law is the universal quantifier, and also the quantifier free part negated. So, and the ingenuity idea is to guess for each possible configuration whether it is reachable or not, and then to verify using item A whether indeed it is reachable, and keep a counter. Counters are good because although the value is exponentially large, right, the graph is exponentially large, binary length of the counter is only linear, and thus we can store a constant number of counters. Let's do that here. And the counter, maintain a counter that keeps track of how many vertices we have A, guessed to be reachable, and B, been able to verify to indeed be reachable. And if at the end of this exponentially large loop using linear memory, the counter value turns out to be equal to the given value, to the known value known by hypothesis n of m, then it means that all our guesses have been correct. And notice that this is a very different semantics of guesses, very different from randomized, right? Because the probability for such all these guesses to be successful is negligible, but we're not talking about randomized algorithm here. We're talking about non-deterministic. So if in the end all the guesses have been correct, right? We cannot, the counter value cannot exceed the number n, because we cannot verify more vertices to be reachable than n, than the actual number. But we can fail to verify, or we can guess incorrectly. But if we have correctly guessed all vertices that are reachable and be able to verify that, that means that also the vertices which we have guessed to be non-reachable must have been correctly without. So that's kind of an implicit, indirect way of verifying unreachability, right? So we guess which vertices are reachable and which ones are not. We forget, of course, we don't store which vertices we guessed, but we maintain a counter. And so if the reachability counter turns out correct, then that means also that the unreachability counter and the vertices which we guess to be unreachable are indeed unreachable. So that's kind of an indirect way of verifying a guess. And if since we excluded the given vertex W from all vertices, that means that this vertex must not be among the reachable ones, and therefore must be among the unreachable ones, and thus follows the correctness of this algorithm. And the linear memory consumption is kind of immediate, since, as I keep emphasizing, the algorithm stores only a constant number of nodes, each one using linear memory, and a constant number of counters, in this case only one counter, again each one counter using linear memory. So that was item B, and then we would proceed to item C, showing that indeed this function is computable in a deterministic linear space. And the proof of that, well, with that proof, of course, the statement finally follows of Immerman-Szelepscenyi, but the proof here turned out to be even more involved. It uses the techniques from item A, which we already used in proving item B, but it also uses the technique from item B of having a loop and guessing every vertex and forgetting for each vertex and verifying, and using the end of the loop counter, to verify whether throughout the loop all guesses were correct. So here's the algorithm, and this time the counter C prime is used to determine the inductively next value n of m plus 1, supposing that we already have calculated and stored n of m. And so again, let me emphasize, we're not going to, in this inductive process, we're not going to store n of 0, n of 1, n of 2, and so on. But we're only going to store the current n of m and the next value. And in the next iteration, we're going to forget the previous one and move on, like our efficient calculation of the Fibonacci sequence, if you remember that. So again, the approach here is to guess for each possible configuration whether it is reachable in this number of steps. And if the guess says it is reachable, then verify that it indeed is. And again, abort if we cannot verify the correctness. But now we need some other way of verifying that our negative guesses, or guess that a vertex is not reachable within m+1 steps, has been correct, because now we don't have the information about n of m+1 at our disposition. Indeed, we're trying to calculate n of m+1. So the other technique is the following. If a vertex is not reachable by any of the vertices reachable for within m steps, then the vertex cannot be reachable in n+1 steps. And we say that again, it's a contraposition. If a vertex is reachable in m+1 steps, then there must be some vertex reachable within m steps and a single edge from that vertex to the new one. And right, okay, let me, yeah. And so we're going to refute to confirm that a vertex is not reachable within m+1 steps by confirming that there is no edge to this vertex from any of the vertices reachable within m steps. And which vertices are reachable in m steps and which ones are not. This is what we can already do according to the technique of item B, and that's what we do here. For every guess for every vertex where it's reachable within m steps. If the guess says it is reachable, then we verify that from this vertex there is no single edge to the new vertex. And then we verify that our guess, which can be done deterministically. Yes, this is something I should emphasize. A single edge, of course, corresponds to, in our configuration, to one step of the underlying while plus program. And this one step can be simulated in a linear amount of memory, because by hypothesis, this is the amount of memory S, it's the amount of memory used by the underlying non-deterministic while plus program. So the current configuration and everything of this program can be stored in a linear amount of memory. Also, this is kind of the induction start when n is equal to 0. That corresponds to the start vertex. And when m grows to 1, that means all the nodes that are, or configurations that are reachable within by simulating one step of the algorithm. So that means when our guess says current vertex W is reachable within m steps, then we make sure that there is no edge from this vertex to our current vertex, and we verify that our guess has been correct using the same techniques by maintaining a count of how many vertices W we have guessed to be reachable, and at the end verify whether this count coincides with a previously computed or given or known number n of m. So, and if that turns out to disagree, then our guesses have been incorrect and we abort. Whereas if we continue, we can be sure that the computation and guesses so far have been correct. And thus, at the end of this inner loop, using the techniques from item B, we can be sure that we have correctly guessed all vertices which are reachable within m steps and those which are not reachable within m steps. And having verified that from none of those reachable, the new vertex W prime is reachable, that means that the new vertex W prime indeed is not reachable within m+1 steps, and thus means that in the outer loop we have guessed correctly here as well. So that after the termination of the outer loop, that means that the value n of C prime is indeed the number n of m+1 of nodes reachable within m+1 steps. So that's our recap of the Immerman-Szelepscenyi proof. with its more and more involved algorithmic techniques of guessing and verifying in a memory efficient way. And now we're ready to move on to a new aspect, namely of the polynomial space, namely polynomial hierarchy. So as you recall, in computability theory, we did already talk about the arithmetical hierarchy and its two aspects, one the syntactical and one the semantical. This is always our two kind of eyes of looking at things. We had the syntactical definition of NP, which means there exists a polynomial size and polynomial time verifiable witness. That's our one eye. And the semantic conception of NP is while plus program with a non-deterministic while plus program. That is one that can make guesses, where the guesses have a semantic meaning of this non-deterministic while plus program. And we've seen that both are indeed equivalent. And in our initial part of computability theory, we similarly had the arithmetic hierarchy expressed one way semantically in terms of Oracle while plus programs, which can use make Oracle queries, for example, to the halting problem, or for example, the halting problem of Oracle programs with halting Oracle, or so climbing up this hierarchy. That was one perspective, and the other perspective was syntactical, in terms of alternating quantifiers ranging over unbounded ranges, namely over all integers. And now we're going to do the same, extend the conception of P and NP to Oracle complexity. So let us recall that an Oracle while plus program can make queries whether current one of its variables xj has a value which belongs to O, where O is a fixed subset of natural numbers, not necessarily a decidable one or not necessarily a polynomial time decidable one. And generically speaking, let's relativize, it's called, let's relativize the complexity classes we've considered so far, P, NP, and P space. And we consider a class of subsets of natural numbers as candidate oracles. Any element of that class, that is any subset of natural numbers which belongs to that class, can serve as an oracle in this definition, right? You see that here. Any oracle from C can serve as an oracle, and P with exponent, this class C, means all the decision problems that can be decided by a polynomial time, a while plus program, which is allowed to make oracle queries to this specific arbitrary fixed but specific oracle. It cannot change oracles. And similarly, we relativize, it's called, in adoption of the terminology from recursion theory. We relativize NP, that is non-deterministic polynomial time oracle while plus program, and we relativize P space, that is polynomial memory bounded deterministic while plus programs that can make oracle queries to oracles, any fixed arbitrary but fixed oracle from this class. So this is now extends our usual complexity classes. And the original complexity classes are recovered, for example, by considering as C just the class which consists only of the singleton empty set. Empty set is empty, and the class which contains only the empty set is a singleton. And why does this recover the original one? Because making oracle queries to the empty set are kind of do not increase the computational power, right? We can replace any such oracle by simply the instruction no, because any oracle query to the empty Oracle will always return no anyway, so we can kind of convert any Oracle while plus program that makes Oracle queries to the empty set by simply the instruction no at the end. So that is means that these definitions really extend our previous definition. Also, let me emphasize that all these the hierarchy that we considered at the beginning of complexity theory, namely that P is contained in NP, is contained in P space, these carry over. That is, they relativize, namely the Oracle complexity class P with Oracle class C is contained in NP with Oracle class C. The same Oracle class is contained in P space with the same Oracle class C. So for every possible such class, one arrives at a similar hierarchy. Relativized P is contained in relativized NP is contained in relativized P space. So why do we consider these oracles? One reason or motivation is that this can serve as kind of hypothetical external subroutines, right? So imagine you purchase some commercial library which claims to be able to solve some hard problem, maybe some P-space complete problem in some way, maybe using some sophisticated hardware, some quantum computer, for example. And then you have no idea how that works inside. It's a black box, but these black box queries are captured by such Oracle while plus programs. Another motivation is Alan Turing's PhD thesis written under the supervision of Alonzo Church, which also considered Oracle Turing machines, we would nowadays say, and in this course we say Oracle while plus programs. This Oracle complexity class captures some problems which we have not been able to or have not located in the original hierarchy, similarly to the in computability theory, the totality problem not being really equivalent to the halting problem, and similarly the problem of minimizing a Boolean function is probably not in NP, but it is actually complete for this complexity class co-NP. Right, so we also relativize co-NP with Oracle satisfiability. So what is minimizing Boolean functions? So following decision problem given a Boolean expression, the kind we already talked about in the satisfiability problem, is it shortest Boolean expression among all those that are equivalent to it, semantically equivalent. So consider another Boolean expression psi, which maybe has the same true and false value, the same truth table as phi, but somehow it can be expressed, its encoding length is shorter, then the two are semantically equivalent. And maybe one such example is an unsatisfiable Boolean expression. A Boolean expression which for all assignments is not true, it's false. And that is semantically equivalent to the constant expression false, which of course is much shorter. So an unsatisfiable Boolean expression is not a minimal one unless it is false. So this is a generalization thus of the unsatisfiability problem, and actually it's a considerable generalization in the sense that it is not known to belong to NP nor to co-NP, right? Unsatisfiability itself is co-NP complete, but minimal Boolean expression is actually complete for co-NP with satisfiability oracle, and since satisfiability is NP complete, that's the same as saying co-NP with any other NP complete oracle here. And now we play our game, see that co-NP, of course, can be satisfied, NP problem can be satisfied by making one Oracle query to an NP, suitable NP problem, and then inverting the answer, which means a polynomial time algorithm having Oracle access to NP, but now this NP in turn must be relativized to NP, and thus we climb up this hierarchy of Oracle, Oracle. So let us collect some properties of this relativized complexity class. Equipping a polynomial time decidable problem with relativizing it with polynomial time decidable Oracle does not increase the computational power, not significantly. It remains within polynomial because the composition of a polynomial with a other polynomial time algorithm that we use to replace the Oracle query with a deterministic one is again a polynomial time algorithm, higher degree polynomial, but still polynomial. Similarly for NP and for P space, we can simulate any Oracle query in this class P space using a polynomial separate polynomial amount of memory, and thus replacing it, the Oracle query, with a deterministic algorithm that only increases the overall memory consumption, but remains within polynomial. On the other hand, what if we kind of mix complexity classes like here or here, then the conjecture says that we climb up the hierarchy, strictly climb up. And this is a conjecture because it generalizes the P versus NP millennium problem. So this is a even stronger hypothesis, but there's also a weaker version, which I'm going to mention on the next slide, namely that the polynomial hierarchy collapses somewhere, which is which follows from P versus NP, but does not imply P versus NP. So here's the polynomial hierarchy. It starts with NP and co-NP and P, as we discussed before. Then there are the class of problems which are either in NP or in co-NP or in both. And then we climb up, as just mentioned, and climb up and climb up and climb up. Inductively, we define delta k plus 1, like in the arithmetic hierarchy, but with polynomial time, to be polynomial time algorithm that can make a queries, polynomially many queries to any oracle in the by induction hypothesis defined class sigma kp, where sigma k is in turn inductively defined as a non-deterministic polynomial time with a sigma k oracle. And similarly, co-NP generalizes to the class k pi k plus 1, with P again indicating that we're not talking about the arithmetic, but the polynomial hierarchy. And so, since algorithm can flip the answers to Oracle queries, it's the same if we use an Oracle in the class sigma k, or if we use an Oracle in the class pi k, because pi k are just the complements, the negation of sigma k problems. And similarly here. And that's our semantic, because it hierarchy, because it refers to Oracle while pass from program deterministic, non-deterministic, co-non-deterministic, making such allowed to make such Oracle queries. And so we can now rephrase the classes that we've already known and discussed about long term here in terms of basic levels of this hierarchy, but also the higher levels, like remember we had this problem minimize Boolean expression, which I said, maybe this is a great exercise actually for you to show that minimizing Boolean formula is in co-NP to the NP and is complete for co-NP to NP. So that means you're asked to construct another master reduction from any problem in co-NP with an NP oracle to minimizing Boolean formula. we're not going to do that here in the lecture. Maybe that's going to be a homework. So, but we're going to collect some properties of this polynomial hierarchy. First observation is that the deterministic classes, the delta classes, are all closed under complement, which is kind of obvious, but yeah, because we can always invert the final result of a while plus program, even when it uses oracles. Second claim is that the deterministic class is contained both in the non-deterministic class and the co-non-deterministic class. Again, remember, we had already these claims for the initial case when k is equal to 0, then, or 1 for that matter, then that's a classical P, that's a classical NP, that's a classical co-NP, and simply kind of relativizing, recalling, repeating the same proof, but now with oracle shows that, and I'd like to urge you to do that by yourself, to recall the proof and see that indeed the proof works and carries over to the case of oracle while plus program, because this is going to be very instructive when we now later move on to the Baker, Gill, and Soloway theorem in today's last slide of today's lecture. So really, yeah, I need to emphasize that you only learn by doing, by proving yourself, not by listening and memorizing all the things I keep saying and all the statements. You have to do the proof by yourself, and this is where you learn from. So the first thing I've asked you to prove is that minimizing Boolean formulas is complete for this complexity class co-NP to the NP. And the second thing I'm now asking you to prove at home is that this inclusion, that the deterministic relativized problem is contained in the non-deterministic and the co-non-deterministic for every oracle actually, and in particular for sigma k minus 1 pi k minus 1 oracle in the induction step of this statement. And going to the other direction, moving on one step up in the hierarchy includes the previous 2 levels. This is again something which is easy to prove, but you have to prove it yourself really to understand that by induction. And so we can move up. And yeah, as I said, there are also problems that are complete for the levels of this hierarchy, like minimizing Boolean functions. So that means these levels really have an important meaning in complexity theory of classifying problems. Like in computability theory, we had to pi 2 as without p as the complexity class for which totality problem is computably complete. And this entire hierarchy with its countably, and actually one can extend it to uncountable ordinals, is all contained in P space. And again, this is something that I urge you to prove by induction as a generalization of our proof that NP is contained in P space. Remember how we proved that? By the way, do you notice how I'm dropping hints for the final exam here between the lines? Good. Right. So every single level on this polynomial hierarchy is contained in P space without oracle. That's a nice thing to prove again by induction on which level in the polynomial hierarchy you are in. Okay, that was our semantic conceptions of polynomial hierarchy, because it would revolve around or based on Oracle white-box programs. Now the syntactic perspective is the one using quantifiers, like in the NP was syntactically defined with this existential quantifier over witnesses. And similar, we can express co-NP as a universal quantifier. This is simply De Morgan's law, right? Co-NP means complement of NP. Complement means existential quantifier becomes a universal one. And the verification part here becomes the complement of the verification part, because the verification part is already in deterministic P. Its complement is again in P, so it doesn't make a difference complexity theoretically. So that we here have this syntactic characterization of co-NP, which easily follows with some logic, contraposition, De Morgan's law, and the syntactic conception of NP that we discussed long before. And here I'm going to introduce this kind of polynomial quantifier range, namely, should be less or equal. All natural numbers whose binary length is less or equal to n, where n denotes a binary length of x. Yeah, let me please correct that inequality. It's going the wrong direction. I'll correct that later. So yes, here's the abbreviation. And now by moving on by induction, that means on relativizing that statement, decision problem belongs to the k plus first level. If and the k plus pi plus first level, if relativizing means there's an existential, or here's the universal quantifier ranging over witnesses of polynomial length, where the verifier is now, by inductive hypothesis, somewhere on the previous level, on sigma k or on pi k. Remember, it doesn't make a difference because we can always flip the result of the Oracle query. And now that's immediate from the definition and relativizing or statement A. But now we can unfold that induction, because remember, here's an existential quantifier and the verifier is in pi k, and pi k, according to this, starts with a universal quantifier and something in sigma k minus 1, right? And so we can kind of unroll this to arrive at the most important, namely the syntactic definition of a polynomial hierarchy is that a decision problem belongs to sigma k, if and only if it has this form of how can we remove that around? Right. If it has this form with alternating quantifiers, sigma k means starting with an existential, then a universal, then again an existential, and so on until the kth quantifier, which is going to be a universal or existential, depending on the parity of k, the level that we're currently considering. And so yes, why these alternating quantifiers? Because remember, when we have two quantifiers of same type, then we can compress them into one larger quantifier over a larger range, but still a polynomial range. So having several quantifiers, consecutive quantifiers of same type, does not really increase the expressive power, nor the computational power, but alternating quantifiers, that really climbs up the polynomial hierarchy in this syntactic characterization, because it says an if and only if. And again, I urge you to prove these statements. They deliberately climb up from very easy theorem A, which is via relativizing B and C, and then applying induction to unroll item B and C together to obtain item D. Where here observe that the final verifier here is supposed to be polynomial time decidable. And right, you may remember that this is kind of similar to the quantified Boolean formula, right? So what's the difference in quantified Boolean formula, where we had these quantifiers? The difference is here in quantified Boolean formula, the number of alternating quantifiers is unbounded, where here the number of alternating quantifiers is fixed. It's k, belong to the kth level. So this is kind of a reflection that quantified Boolean formula will prove to be complete for P space. P space, we said before, contains every single level, every individual level of a polynomial hierarchy, in particular the kth level. And the kth level in turn is characterized by having a constant, namely a k number of alternating quantifiers. So that's a subtle but important difference. What is not really a huge difference is that these quantifiers here now range over natural numbers of polynomial length. Well, it is relevant here. We cannot restrict here to bits. Well, yeah, I'm not sure whether we can restrict to 0 ones here. But anyway, so the long time message here is this is this syntactic perspective is a natural restriction of quantified Boolean formula, in the sense that now the number of quantifier alternations is constant. It's k and no more than k, whereas quantified Boolean formula, it's unbounded. It can be linear, can be polynomial in the length of the input. And thus intuitively, these problems here should be easier. At least they're not more difficult because the polynomial hierarchy is contained in P space. So why do we discuss all this? I mentioned an important application being on the last slide of this section, which we're now heading for, namely approaches to solving the P versus NP problem. So if you're eager in earning the $1 million for the Millennium Prize problem, then this is where you really should start listen up. And we say it again, this is the part which is crucial for solving the P versus NP problem, because it tells which approaches provably cannot solve the P versus NP problem, right? So remember, Gödel's theorem says there's a statement which provably cannot be proven. And here we see statements which say that provably these kind of proof techniques cannot solve P versus NP. And this is kind of an explanation for why throughout 50 years, we have not been able to solve P versus NP, because for several decades, we have tried these very proof techniques. And now using the paradigm of Sherlock Holmes, what does Sherlock Holmes say? Exclude everything impossible, and then what remains, however improbable, is going to be the solution. And the same is going to be true for the P versus NP. Here we see a large class of proof approaches which provably cannot solve P versus NP. So let us, I urge you to focus on the remaining, however unlikely they are. So what is this proof techniques that provably don't work? It's relativizing proofs. And that means proofs that give relations between complexity classes that carry over to the relative complexity classes with Oracle. I've mentioned such proofs before. So P is contained in NP, which we proved at the beginning of this second part. And P with any oracle is contained in NP with the same oracle. So that proof relativizes, and I urge you to repeat that proof to see that it relativizes. NP is contained in P space. We proved that at the beginning. NP with respect to an oracle is contained in P space with respect to the same oracle. This proof relativizes. Please recall and redo that proof. So these are oracle relativizing proof techniques that also work with oracles. And another example I'd like to more involved is the Savage theorem. NP space is equal to P space, right? We discussed that early in this chapter 5. And the same holds, it relativizes, the same holds true for every possible oracle A. And I want you to verify that, to recall and reanalyze the proof of Savage theorem, that it really works also for oracles. And why is that important? Because there are oracles where P is actually equal to NP. So that means that's the first statement. There exists an oracle such that P relative to that oracle is equal to NP relative to that oracle. And that's a huge bummer, because it means that any proof technique that carries over to oracle will not be able to prove P different from NP, because with relative to that oracle, it would prove something wrong, right? Does that make sense? So there exists an oracle such relative to which P is equal to NP. So we cannot use relativizing proof techniques to prove P different from NP. Well, can we use these techniques to prove P equal to NP? Unfortunately, neither that. So namely, there exists an oracle. Admittedly, and these are artificial oracles, but still there exists an oracle such that P with respect to that oracle is provably different from NP with respect to that oracle, meaning that, again, relativizing proof techniques cannot prove P different from NP. Item A says they cannot prove P different. Item B says they cannot prove P equal to NP as long as they're relativizing proof techniques. And most of the proof techniques we've seen so far in this lecture are relativizing. There's so this statement I and B are due to Baker, Gill, and Soloway from 1975. There's a strengthening of item B, namely, not only does there exist such an oracle. Well, let's quickly get item claim A out of the way. That's because that's easy. Quantified Boolean formula is such an oracle, or any other P-space complete problem. Why is that the case? Well, if you can make oracle queries to P-space complete problem, then means that P relative to P-space, that's simply the same as P-space itself, right? It obviously contains P-space because we can simply relegate any input simply to this P-space problem. If it's just P-space complete, we can reduce it in polynomial time to the problem under consideration. And of course, it also cannot contain more than P-space. So when the oracle is P-space, here we have P-space, and here we also have P-space, because remember, NP is contained in P-space. NP with oracle P-space is contained in P-space with P-space, which is P-space, as we discussed before. So this is kind of an easy construction. The interesting construction and involved construction is item B. But we're not going to prove that. Instead, we're going to prove a strengthening of claim B. Namely, we're going to prove that almost every oracle has actually make P different from NP relative to that oracle. This more formally, let's consider random oracle. Then with probability 1, with respect to that random oracle, P is different from NP. What do I mean with the random oracle? I mean this following random process. For every natural number, flip a fair coin, probability 1/2, independently. And if the coin flip says that head, then put that natural number into the set B, and if the coin flip reveals tail, then remove that natural number from B. So every natural number, whether it belongs to B or not, is decided by randomly, independently at random. That's what we call a random subset of natural numbers. And then we have a probability distribution on that, right? It's the product distribution, which is also kind of like the standard measure on Cantor space, right? Cantor space is a space of infinite binary sequence. So every position in that sequence corresponds to a bit. The nth position, bit 0 or bit 1 in the Cantor space sequence, says whether n belongs to the set B or not. So that's our kind of a notion of random oracle. And the statement says with probability 1, so almost every oracle except for a set of measure 0 will result in P with respect to that oracle being different from NP with respect to that oracle. And this, of course, immediately implies the claim B, right? Because if almost every oracle, then in particular, there exists an oracle trivially so. And we're going to prove item C on the next and final slide of today's session. So please stay tuned. This is getting more and more involved, but we're also approaching the end of this chapter 5. There's recently right. So this is item C is due to Bennett and Gill, 1981, 6 years later. But this is like, 40 years ago. And rather recently, like 6 years ago, Rossmann and others have proven a considerable strengthening of item C, namely that the polynomial hierarchy is infinite with respect to random oracle. So remember, the polynomial hierarchy is kind of an extension of the P versus NP problem. So if we could show that the polynomial hierarchy is tight, is strict, then it would follow that P, in particular, that P is equal to NP. There are some possibilities that the polynomial hierarchy could be finite. That means it collapses, it stagnates at some level, at some kth level. But what Rossmann and others proved that if this happens, then it's again something specific to the non-relativizing proof, because with respect to relativizing proof, with respect to random oracle, that means basically with respect to almost every oracle, this hierarchy is infinite and climbs up infinitely high. So that's this is really state of the art. Very recently, we're not going to prove that. We're going to prove item C, and then we're going to conclude this chapter 5 and end with a quiz. So please stay tuned as I present to you a streamlined version of the proof of Bennett and Gill. So here's, for your convenience, again, a reminder of the statement itself. With probability 1, random oracle has P different from NP. So, and we're going to actually construct a decision problem and prove that to belong to NP with oracle B, but not to P with oracle B, right? So this is really approaching the millennium problem, right? Constructing a decision problem which we can prove to belong to NP, but not provably does not belong to P, cannot be solved in polynomial time, except in this case, we're going to do that with respect to the random oracle B. And of course, the empty oracle, which recovers the original classes, the unrelativized classes P and NP, is not a random oracle, right? So the empty oracle is not even related to the randomized. So, but here's the decision problem, right? So the decision problem, of course, depends on the oracle B, and it's this one. The decision problem contains only numbers that are integer powers of 4, and such a number is defined to belong to this decision problem if and only if there exists such a, imagine this to be a witness of value at most 2 to the n. So the length of that witness is at most n, which is a linear in the length of x. The binary length of x is 2 times n, right? 4 to the n highest binary length 2 times n. And then there's another condition, namely universal quantifier. For all z less than n, this number must be contained in the oracle B, which is a subset. Okay, this is all very artificial and confusing. So let me first of all point out that this, whatever the oracle, so this is really regardless of what is the oracle B, this decision problem belongs to NP. So recall, NP means there exists a witness of polynomial length that can be verified in polynomial time. And here we have this witness. So namely, y is the witness. I already explained why it has polynomial length, actually linear length. And the witness condition here, that's maybe a little bit off-putting because it involves this universal quantifier, but the universal quantifier ranges only over a linear number of steps, right? So this one ranges over exponentially many candidates of polynomial length. This one ranges over linearly many candidates. So this is not really computationally hard to verify. This is the hard part. And indeed, this property can be verified in polynomial time by a verifier that, of course, needs to have oracle access to the oracle B in order to verify it. How does that verifier work? Well, it tries all possible values for Z, of which there are only linearly, polynomially many. For each one, calculate this expression, which is easy, right? Binary length is not really large. This is the input, right? This input. And then queries the oracle repeatedly, linear number of times to verify. So long story short, this is, of course, belongs to the class NP with oracle B. Okay, so that's that's first part, but now we need to show that this decision problem cannot be decided in deterministic polynomial time with the oracle B, and for random oracle. And this is the involves this. This is the ingenuity, and to get to there, let us have a graphical depiction of this of these expressions. So here you see a view of the line of natural numbers. So here's 4 to the n, one candidate element of the set. Here's 4 to the n plus 1, another candidate. And now let's see whether and which of these belong to the set. That depends on what is that here. This corresponds to kind of segment of successive natural numbers of n successive natural numbers. So here's 4 to the n plus n. This is the first block of candidates Z, right here. Then there's 4 to the n plus 2 times n. That's the next candidate corresponding to, the first corresponds to y equals 0. The next one corresponds to y equal 1, right? And the next one corresponds to y equal 2, and so on until the last possible, that's where y is equal to 2 to the n minus 1, must be strictly less, times n, and always the next n successive elements are what are considered here in this black box, right? And whether these elements are all present, that determines whether the argument x belongs to the set or not. All these n consecutive elements for some y. So imagine this to be all these intervals having the same length n, and the question is whether there exists the exponentially many intervals, whether there exists such an interval that entirely is contained in B. So that's a graphical representation of this algebraic condition. And what I want to calculate now is, since we have a random oracle, what is the probability for this condition in the box to be true? And the first simple observation is that this is a very small probability, right? So remember, our random process picks and inserts a natural number into this random oracle with probability 50-50. And the next element in that interval also 50-50, and so on. So for all of them, for all n of them to be present, that means since the random process is independently at random, that means the probability is 2 to the minus n, right? Regardless of what y is, this does not depend on y, it's just because this interval contains n natural numbers, and all of them contained for all of them to end up in the random oracle means that n times the random process in constructing the oracle must have resulted in a heads-up coin flip. So that's a easy analysis, but now let's analyze and include also the quantifier over y. Let's now fix x and also ask what is the probability for x to 4 to the n to belong to such a this oracle, random oracle. So what is the probability that there exists such a witness? And observe that we cannot just use the union or the sum of all these. Well, because that's the sum is only an upper bound to the probability. Instead, we proceed, we move on to the complement of that problem, of that event, right? So the complement of the event says for all y less than 2 to the n, there exists a counterexample. And the probability for this is, of course, 1 minus 2 to the minus n. And now with the universal quantifier for all, we can harness independence, right? So for every y, the rest of the condition here is independent because it revolves around disjoint intervals here, right? So whether some elements belong to the oracle or not here is independent of whether which elements here belong to the set. So long story short, this is a probability for this part to be false. And that's the universal quantifier here. It means by independence, doing that, multiplying that as many times as their universal quantifier ranges, which means 2 to the n times, and then returning to the original unnegated problem means 1 minus, right? So we proceed to the complement event and then use independence and then back. So this is really equal. This is the probability for that. And now if you recall, this is basically the definition of the exponential function. So this converges quickly to 1 over e, and thus 1 to 1 minus 1 over e. That's mathematics. You know mathematics, I don't need to elaborate that, which is roughly 0.63. So summarize, for sufficiently large n, we can say that the probability of 4 to the n to belong to this set, depending on the random oracle, is roughly 63%. It's a constant, that's a message. And now we can show that algorithm cannot decide this set in polynomial time, even if the deterministic algorithm has oracle access to the decision problem B, at least not in polynomial time. And intuitively, what's the intuition? Right, intuitively, for an algorithm to check whether x equal 4 to the n belongs to the set, it must, again, as with any NP problem, check whether or not there exists such a witness. But there are too many witnesses to verify in polynomial time. And that's the intuition. The information that we now have here is that the oracle really provably requires a program to check all these. That's the difference, right? If we can prove that without the oracle, then we have proven NP different from P. But here we have this oracle, and we have important information theoretic properties, namely changing the oracle here, changing one element of the oracle, removing one element here means spoiling the entire interval, right? So intuitively, an algorithm must really look at every single element here, because otherwise it would make an error. And same here, and same here, and same here. And now let's make that formal. So let's call this the query Q, the kind of query that the purported algorithm in our indirect proof makes. And let's consider what that algorithm makes on input 4 to the n. Can make at most polynomially many such queries to be queries which we can, without loss of generality, suppose to have this form, because this is a unique decomposition here, right? Also, let me emphasize that there's some gap here deliberately to the next stage, 4 to the n plus 1. That's important. That's how these numbers were chosen, so that the last interval here ends at this number plus n, which is strictly less than 4 to the n plus 1, the next number. So there's no kind of overlap between different arguments. And this is what we now exploit here. And we show that with, observe that with this probability, the current algorithm makes a mistake. What does it mean to make a mistake? It means the algorithm on input x accepts under the condition that x actually does not belong to the decision problem. That's what it means for the algorithm to make a mistake. Or the algorithm could reject under the condition that x actually belongs to this. So these are conditional probabilities, all with respect to the random oracle. And we're going to show that both these conditional probabilities are positive. Right. And therefore, there's a positive probability that the algorithm makes a mistake on input x. And then we take the independence and again proceed to the complement and so on to make sure that there's a with probability 1. So with this probability, the algorithm errs on this particular input. So we fix the algorithm. We make a random oracle, and then we analyze that the algorithm has this probability of making an error on this oracle, on this particular input. And therefore, once we let the inputs vary, that means the probability that the algorithm makes an error on some input tends to certainty, or rather the complement event, the probability that the algorithm correctly decides, let me say the probability that the algorithm correctly processes this particular input is strictly less than 1. And by independence, the probability that the algorithm correctly decides all possible inputs is going to be the product of all these probabilities less than 1, and this product of probabilities less than 1 tends to 0, and thus the algorithm with certainty makes some mistake on some possibly sufficiently large input. And this is uses the condition, the observation that the algorithm can make at most polynomially many queries, which is less than the number of queries it intuitively information theoretically must make as n is sufficiently large. So when the asymptotics here kicks in, that's when these properties all hold, and thus the algorithm with certainty makes a mistake, and that holds for any possible polynomial time algorithm, and thus we conclude that there cannot exist a polynomial time algorithm that deterministically solves this artificial decision problem within polynomial time. So yeah, that's already time is up. I have to postpone the quiz to next time. So thank you very much for your attention, and see you next time.